everybody. For me, it's a pleasure to be here with you, sharing this talk about industrial AI from automated process to cognitive analytics. My name, as the moderator said, is Diego Galao. I'm professor of condition monitoring in Luleå University of Technology. And basically, what I'm going to give during this 40 minutes is what is the relevance of the industrial AI and what is the maturity in terms of analytics. We have to be aware that AI, that everybody knows here, is the ability of the computers to do certain tasks without human intervention. This is clear in all the domains, but especially during the Industry 4.0 revolution, we have been developing new techniques just tailor-made for the industry. That's why industrial AI is the application of this AI, of these technologies, to specific industrial assets in order to increase the value creation of these assets, improve the productivity, and improve the profitability of these assets. In general, we have to be aware that Industry 4.0 and industrial AI, they have been navigating together during these last 10 years. And the data that we are working with during these 10 years has grown up a lot. Actually, we have to admit that the equipment, the assets are real data driven, and the industry needs the AI to become pure data driven. However, the methods, the AI in the industry is not new. We have been working with neural networks, with support vector machines, for many years, doing some classifiers, doing some clusters, etc. What is new now? What is new in this industrial AI time? The first thing that we have to consider is that we have failed in one point. A few years ago, we thought that the AI was going to be populated in the industry in a very, very massive way. However, last year, we realized that the scaling up process of this AI has not been successful. Still, most of the projects that we have in the industry, they are pilot cases or demonstrators. And this is because maybe we have not gained all the confidence we needed for the AI in the industry. Also, we have to be aware that when we talk about consumer AI, we have the typical prediction or profiling of customers. We have the typical statistics approaches to predict where you are going to buy. You like this book, you like this movie, then you are maybe candidate to be offered this service. This is the traditional profiling when we are talking about AI in the consumer market. What happens when we talk about industrial AI? Our assets are different to some extent, but they have some similarities with humans. They need some profiling, they need some predictions, especially in terms of the remaining useful life of these assets. We need some fleet management because we have many assets of the same type. And at the end of the day, what the services that we are going to provide to these assets are quite similar to the ones that we provide to the end users, because the assets, they need some profiling, some predictions, and definitely some services. If you take the traditional consumer type, what is the data that the AI engines they are working with? Text, images, videos, etc. What is the difference with the industrial AI? The industrial AI, we work with sensor readings, we work with pictures, we work with time series, but basically the problem is that in the machines, we are working with machine-generated data. In Google or Facebook or Amazon, we work basically with data produced by humans that is maybe smaller in amount but much richer in information. In the industry, we work with data that is much bigger in terms of amount but maybe smaller in information. That's why the pipelines that we have to consider are a bit different. Of course, customer segmentation, profiling, prediction is much easier when you have a lot of data and very rich in information. It's not the case. Here in the consumer profile, we have maybe small data sets, but it's very rich in information. In the industry, is the other way around. We have large data sets, but the information that we have is reduced. That's why we have to consider this, because we will have some pros and cons when we try to import from the consumer side some AI algorithms to the industrial side. And what are the elements that we have in the AI process? The elements that we have in the AI process basically are three. We have the data, we have the infrastructure to process the data, and we have the analytics, the models in this infrastructure. Then let me go one by one, looking the issues and challenges of this. What is the challenges in terms of infrastructure? In terms of infrastructure, we have to be aware that where we perform the industrial AI, we have basically three different types of industrial AI infrastructure. Basically, we have to be aware that we can perform in normal servers, in cloud, or in the asset. We have different configurations because the different places where I can perform the AI is entirely different. And the performance of these algorithms and the outcome of these algorithms will be entirely different in function of the infrastructure that I have for. That's why it's extremely important to see where I can perform this kind of analytics. For example, if I go for a fully centralized decision system, that is maybe the most traditional one, each asset is sending everything to a server or a cloud. I perform the analytics, the AI algorithms in my server or in my cloud, and I distribute the decision and I populate whatever I have decided. This is the traditional approach. The semi-centralized is where I have some intelligence on site and some intelligence in the cloud or in the server. This is really good because then I'm, let's say, making some kind of software computing in the cloud, and I'm not sending massive amount of data to the cloud or to the server, and in terms of energy and bandwidth is more economic. But we have to be aware that this architecture, where I have some intelligence, for example, in our cars, or some intelligence in our cloud, this combination makes our infrastructure a bit more difficult. Of course, the ideal situation would be a fully decentralized decision system, where the asset itself has the intelligence and doesn't need any connection to a cloud or a server, and is able to manage all the analytics without any connection. This would be great, but unfortunately, the performance of these algorithms without any connection with peers or with cloud would be terrible, because we wouldn't be able to put any added value from one learn, all learn, etc. That's why we have to balance which one is better. And in terms of industrial transport, we have to be aware that maybe a combination of cloud and server with some edge computing, where the asset is partially intelligent, would be the best solution. Definitely, we have to abandon the solution of pure cloud or pure server based, where the assets are totally dummies and they are sending the data to these places, because this doesn't work. Actually, we have to be aware that the trend now is to move towards edge computing, because if I can deliver some services on edge and I can reduce the amount of data that I'm transmitting and the energy that is costing my transmission, definitely is much more efficient. The only thing is that I have to balance the services between this kind of configurations. We have to be aware that now the architecture has evolved a lot. Actually, in the traditional way that we had in the past, for example, if we had a fleet of trains, all the trains were transmitting to the cloud was performing the decision or the algorithm that was in place, and the decision was transmitted to each member of the fleet. This is extremely consuming in terms of bandwidth and energy, and this has to be abandoned. This solution is no longer a good solution. What is the best solution now? The best solution is each member of the fleet is performing analytics, and what I transmit to the cloud is the model. The model that is individually is tuned in each asset. Once in the cloud, the models are automatically analyzed, and the top performer is populated along the fleet. In that way, if I have one element in the fleet that is learning with a very high performance model, this model will be populated all over the fleet, and we will not transmit huge amount of data, but just transmitting the model will be enough to populate the good practices and the lessons learned. This kind of federated learning or distributed computing is extremely good in terms of multi-agent to reduce the bandwidth and have a combination of cloud and edge computing, what we call the concept of fog computing. What task I can perform at the edge? At the edge is, of course, nobody wants to put a huge intelligence in the edge computing because it's expensive and maybe it's not efficient either. But what task I can perform at the edge? Definitely, the task that I can perform is feature extraction. I can perform some clustering. I can perform some data cleaning, some data preprocessing. Then why I'm going to transmit the raw signals to the cloud and consume a lot of data with that. This definitely is not good. We don't have to consume that amount of bandwidth and energy. We have to be aware that maybe with this kind of mix of edge and cloud, we are able to compensate this. Then what we do is basically we have some services like feature extraction, etc. We have these services on the other edge, and then these services that are not added value services are transmitted to the cloud. In this case, we have to be aware that the traditional approach is totally gone, and now what I do in every element of the fleet is I train the model, and what I export to the cloud is the model. I export the model, and the cloud will analyze which model is working better and will populate this model. Definitely, this is the infrastructure that I have to be aware. What is the second element besides the infrastructure? The data. What data I can work with? Basically, we have the operational technologies data, the sensor data, PLC, etc. When I perform analytics for industrial AI based on OT, operational technologies, is very easy because I have the data coming directly from the field in the way of sensor readings or PLC or SCADA, and I can introduce this into some kind of machine learning for some kind of classifier, clustering, or some kind of forecasting, regression, etc. What is the plus and minus points of this? The good thing is that you can have a real-time analytics that you are performing based on the sensor readings, and you are delivering some kind of service. The problem is that this kind of operational technologies, the sensor readings, are disconnected from the different events that happen to the asset. Basically, it's the OT. It doesn't have any kind of clue about the maintenance performed to the machine or the different operational profiles, etc. Then basically the operational technologies is very limited and just useful in some kind of assets where the operational technologies have been very successful. For example, the wind farms have been very successful just doing analytics with data coming from the operational technologies, basically data from the PLC and sensor readings. But what about the IT systems? The OT is the sensors coming, the readings coming from the sensor, PLC, etc. But in the higher level, we have the IT systems. The IT systems where I have my ERP, my CMMS, my MES, etc. What do I need to combine this IT data with the OT data? This is the real thing that we have to consider. The IT data needs to be combined with the OT data. Basically, this is what we need when we combine taxonomies and ontologies. Taxonomies is the breakdown of the asset. What do I mean? What do I mean with that? It's basically, if I have a wind farm, the wind farm is not some kind of silo. I have different components inside. I need to know the data from which component is coming from, and then I will be able to select and cluster which component is having the problems or eventually needs some kind of repair. But more important are the semantic ontologies. The semantic ontologies is the way to describe the reality. For example, in maintenance, if I have one wind farm and this sensor reading is giving some abnormal vibration, and this triggers that I shut down the wind farm, And this shutdown triggers that I send some maintenance crew, and the maintenance crew launch some kind of purchase order for some spare part. All these actions are combined together, and the graph theory, for example, they can describe the reality of maintenance with all these kind of events. It's not just a matter of a sensor reading, it's a matter also of different events that are linked due to with graphs or other semantic ontologies that we can create. That's why the convergence between OT and IT is crucial to describe the reality. Actually, the convergence between OT and IT is crucial in order to describe not only the reality of the asset based on the data that we are capturing from the sensors that are on board of the data, but also the data that is coming from the workshop, the data that is coming from the different dealers, etc. Basically, what we have to be aware is that the operational technology data coming from the sensors, when we merge and we create the ontologies with the IT data, we are able to create some metadata that, doing analytics on this metadata, we can get much better performance in terms of predictions and prescriptions. Definitely, the convergence between OT and IT is absolutely needed in order to offer a good analytics. And what else in this convergence is missing? Definitely the engineering technology, the ET. What do I mean with the ET? We are talking about the data from the sensors. We are talking about the data from the IT, from the information technology. But we need also data that comes from the knowledge, from the experience of the crew, from the experience of designers and manufacturers. This convergence between IT, OT, and ET, the engineering technology, is configuring the complete data set that we need for our analytics. In this case, we have to be aware that we need three types of data that are different data silos. On one hand, we need the historical data. That is the data that we are collecting from the field, sensors, etc. We need the knowledge that is the the knowledge that we have from engineers, maintenance crew, designers, manufacturers. And finally, we have one more data set, the surprises. Unfortunate events that happen time to time, that we will talk about this later, but these surprises, they configure the learning process with our analytics. And finally, we have talked about infrastructure and about data, and now the analytics. Which kind of analytics I can perform? The analytics that I can perform, everybody knows that the analytics go from descriptive analytics to cognitive analytics. And definitely in this, we have to be aware of the difference and the challenges that we have when we perform this kind of analytics. If I'm getting industrial data from one asset and I want to perform descriptive analytics, basically when I do descriptive analytics, what I do is anomaly detection, is having one data set, and in this data set, I can see that some elements belong to some normality, for example, and some elements belong to some abnormal behavior or some outliers. What is this? This descriptive analytics is maybe some kind of normality model. I'm able to say that something is going different, not wrong, different from the process. What does it mean? That I can detect anomalies in my data set. Anomalies in my data set that can be point anomalies, contextual anomalies, or collective anomalies. What do I mean with this kind of anomalies? Point anomalies is the anomaly that we are dreaming. We have a data set that is very compact, and we find one outlier that is clear. It's clear that is one outlier, and we can see this outlier crystal clear. This is the perfect anomaly that we can detect. But this is not very common. Many times we have the contextual anomalies. What does it mean? The contextual anomalies is when one anomaly is produced just in certain operational context, but not always. And this makes my life a hell, because I have to see which context is the one that is triggering that anomaly. And finally, we have the collective anomalies. That is maybe the nightmare of the descriptive analytics, because in that anomaly, all the elements are anomalous. It's like, okay, you go to a place and everybody is wearing glasses, and you infer that all over the world everybody wears glasses. This is very unfortunate because you start from classrooms. And what is the challenge in descriptive analytics? The challenge in descriptive analytics is the context. Why the challenge in descriptive analytics is the context? Because if I have one anomaly that is happening just in a specific context, the problem is that when the context changes, this anomaly may pop up. And this is for me really bad because I may mistake this anomaly with a failure. And this is the main problem that we are going to find. That's why we have to define context awareness, that, okay, this anomaly is working in certain anomalous scenarios. We have to be aware that the context sensing for descriptive analytics is crucial. There you have a picture of a mining track. I can tell you that the mining track, if you look the sensors of the mining track, is entirely different if the road is good or the road is bad. The track is the same, but the readings of the sensors are entirely different. That's why context is extremely relevant. And in this regard, you have to be aware that, for example, let me pinpoint two quick examples. You have there the railway context, one train that is going up or going down in one slope, or the rail track is bumpy, or the temperature. The readings of the sensors are entirely different. Same in the maritime context. If you have one engine, you may get some anomalies, and this is not due to the engine itself. It's due to the waves, the height of the waves, the quality of the sea. That's why if we don't cluster the anomalies according to the context, we will get contextual warnings that are mistaking my readings together with failures. And this is the problem, that we have to be aware in which context this kind of anomalies are detected. That's why all the data that we are collecting in the organization, we have to be aware that many times data that we are not using for anything else maybe is used as context engines to separate contextual scenarios where anomaly detection is triggering some readings, or contextual scenarios where normality is total. That's why it's important to see context as a challenge of the descriptive analytics. When we go to diagnostic analytics, is one step ahead. This diagnostic analytics is not only to see that we have two clusters, I have normality and some abnormal data, but I'm also able to say, okay, this cluster is normal and this is this failure. Means that in diagnostic analytics, I'm able to identify also, not the anomaly, but also identify what is the cause and location of this anomaly. In few words, I'm identifying what is going on with that anomaly. In this case, the problem that we are facing is a huge problem because the data that we have in our records is very poor. And if you take all possible failures you may have in your system, and you take the data that you have, may cover around 20% of the total failures you have in your system. What does it mean? It means that you will be able to recognize just the 20% of failures that you have records. The 80% of failures that you don't have records, you will not be able to see which failures are happening. And this is what we call the black swan in diagnosis. Black swan is the challenge for diagnosis, because the black swan for us is one event that I'm not able to recognize. The black swan is one event that is completely unknown for me. It's one event that I don't have records. It's one failure that never happened in my system. And suddenly this failure is popping up. Maybe if I'm lucky, this failure that I don't have records will not be very harmful, but maybe I'm really unlucky and this failure is extremely harmful and I didn't have any clue to detect this failure. That's why when I have some kind of lack of knowledge and this kind of unknown, this black swan pop up, then my diagnosis capabilities are very, very low. And we have to be aware that the black swan events, you don't have to think about earthquakes or about Fukushima or about the Gulf of Mexico. You have to think just about failures that you have in your system that never pop up. And you cannot recognize these failures when they do. That's why when they pop up, these failures are rare because you don't have any kind of data. They may have one extreme impact, and when they happen, you find the explanation backwards. They have retrospectability. That's why we have to be aware that the black swan losses is maybe one of the most important challenges that you are going to find in the case of diagnostic analytics. And diagnostic analytics, unfortunately, is more and more common because the data that we have from our assets basically is normality. And the normality has a lot of data, but no information. That's why the black swan is a real challenge for diagnostic analytics. And in industry and transports, unfortunately, since we have very reliable stuff, the data sets are much poorer and poorer in terms of information. That's why the black swans are extremely relevant when we want to have this kind of challenge, okay? The third type of analytics is predictive analytics. Predictive analytics is not only to say I have two clusters, not only to say this cluster belongs to type A and this cluster belongs to type B, and this is A and this is B, and I know what is going on in A and B. Now, what I want to predict is how to move from the cluster A to the cluster B. And this is the predictive analytics. Basically, if I have healthy information and I have unhealthy information, how long will take my system to move from healthy to unhealthy, what we call the remaining useful life of our system. And in this case, the challenge that we are facing is the challenge of the picture of Dorian Gray. Basically, this is the challenge that we have when we try to predict the future based on the past. And what do I mean with predicting the future based on the past? Is the data that I already have is the data of my past. And if I have all the data from my birthday until now, I have a bunch of data, and I can extrapolate these models to predict my future. But are you sure that you can do that just with the data of my human, let's say, brain? Definitely no. Why? Because when we have this kind of approach, the blue area is the comfort zone. I have this data, okay? I have this data and I can predict everything in this data because I know how my asset behaves in the blue area. It's the comfort zone. It's the comfort zone because I have already observed how the assets behave until certain age. But if I want to go beyond that, if I want to see how I will look like in 50 years, I don't have any clue about that. I cannot extrapolate the models that I have. However, if you look at the picture of Dorian Gray, this guy wanted to be forever young and see the aging effect just in the picture. And this is what I want, because predictive analytics, I want to keep my assets as good as new and just looking the aging in my system. Then how to do that? Definitely, this is what we call also the Swan zone. How to see the moment that the swan is going to pass away. How can I see that? In this case, definitely, we need a co-creation between the data science and the engineering technologies. Why I'm saying that we need the co-creation between data science and technology? Because the information that I have from the past is really good for that comfort zone that you see in the first part of the graph. But when I go to the second part of the graph, I have a lot of uncertainty because I don't know how my asset is going to behave in advanced stages of degradation. That's why, as you can see in the flow chart, you need the test data, but you need also the background and health knowledge. And what does it mean? I need also the models, the physics of the failure, to see how my body is going to behave onwards, because I don't have data reliable enough to extrapolate models from my past to my future. And this is where the physics of the failure comes into the picture. I cannot make accurate predictions and certain predictions if I don't introduce model-based in my approach. And this is where the data-driven approach get merged with the model-based. Basically, it's a hybrid approach, hybrid models where data-driven models get merged with physics of the failure, and the data sets are much better and much more complete in order to perform much better analytics. Basically, in this regard, what we do is we bring the physics of the failure to complete the incomplete data sets and to compensate the lack of knowledge that I have due to my lack of knowledge or due to a small number of observations in the past. In few words, if I want to see how I will look like in 30 years, I cannot use the normal models that I have now, because the aging of myself is not it cannot be extrapolated with the past models, and I need to introduce from now onwards the physics of the failure, that is the inherent information in my body, in order to complete these data sets. And this is maybe the biggest problem, the biggest challenge in predictive analytics. Finally, we have prescriptive analytics. Prescriptive analytics is one analytics really, really interesting. It's not only the prediction of the remaining useful life, it's the prescription. What does it mean? If you have one asset, for example, your car, that is suddenly you are getting one warning that is you have one problem in the engine, and this is not going to last for many kilometers, then what to do? Maybe you should reduce the speed and get the next petrol station or the next workshop, or maybe you should shut down your car and call the technical service. What to do? Because when we get a warning, you have multiple choices in terms of actions, and the prescriptive analytics has to help us in order to see, okay, this operational profile is more aggressive, the remaining useful life will be consumed faster, and this is maybe softer, and you can afford maybe to run your asset for long. Then this is what is the challenge when we work in prescriptive analytics. Is the challenge is what we call the digital butterfly effect. What do I mean with the digital butterfly effect? The problem is that we have a bunch of data, and the data that we have is huge. The industrial AI should help us to see the invisible things in this data. And definitely, if you have to prescribe what is better for your asset, you need to consider multiple scenarios with multiple choices where the asset is going to have a number of possible solutions in terms of operation and maintenance. In order to find the best one, the industrial AI has to dig into this data. And for that, this data, the data that I'm providing, maybe is not enough. We have to go deeper and see what additional data may be interesting for us in order to compensate this kind of complexity that we are having now. Because the key problem of the digital butterfly effect is, okay, if I want to prescribe something for my machine, because my machine is having a problem, and I have to prescribe the best operational profile and the best maintenance solution, the key problem is my machine learning model enough? Because how much data I should consider around my machine to create the best prescription for my machine? Actually, when we work in the industry, maybe the link between my prescription is my machine in India connected with a machine in US connected with one machine in India or in Europe. Basically, what I mean is that the data set that we are working for predictive diagnostic and descriptive analytics was rather small. But now, for prescriptive analytics, the machine learning model has to compress a much bigger amount of data and a much more complex model. Because now, when we talk about assets in a global supply chain, the assets are connected and the decisions are also connected. That's why we have to be aware that the prescriptive analytics has to keep up with this complexity, and this is not really easy. That's why we have to be aware that the need for complete data sets is when I take the data from the sensors, I take the physics of the failure, I take the context to compensate the problems that I had in terms of descriptive analytics, the surprise that may come from different black swans, and the hybridization of all these data sets will create a data set good enough to perform this kind of analytics. That's why when we move to the final step, that is the cognitive analytics, where the prescriptions should be taken in automatic way, without any kind of human, then we have to be aware that the complexity and the AI, they reach the maximum level. We cannot go for cognitive analytics where the prescriptions are taken automatically if we are not able to have real good data sets and real machine learning algorithms that keep up with the complexity of this data set. We have to be aware that the next step of the industrial AI is the servitization. When we reach the level of cognitive analytics, what we want to deliver is services. Industrial AI in these companies is there to deliver services. And the services is basically failure forecasting and performance monitoring. If we are not able to deliver this for very huge number of fleets, we will not be successful. We have to be aware that after COVID-19, the large fleet, they don't need humans anymore, and we have to be aware that the large fleet should be autonomous for unmanned systems in order to perform self-maintenance and be able to run without or with the minimum human intervention. In summary, let me say that as concluding remarks, that the data is maybe one of the key factors in analytics. I think we have very good machine learning and industrial algorithms, but the data that we are training is very poor. The industrial AI cannot just keep up with this complexity collecting data from the sensors. We need hybrid models in order to compensate the lack of knowledge that the sensor readings they have. Definitely, data-driven solutions may be good, but only if you have all your failures in your records. If not, don't take decisions based on these analytics. You may have huge problems. And after COVID-19, we have to be aware that unattended and unmanned systems are crucial. That's why in this case, the industrial AI will get much more relevance, and cognitive analytics is not an option. We have to go there, and for that, we have to overcome all the challenges that I mentioned in the different analytics. Thank you very much. It has been a pleasure to have this chat with you, and I will be now very happy if I can answer some questions from you.
Thank you so much, Diego. It was a pleasure having you today. I'm just checking. Currently, we have one question. We still have a few minutes. Maybe we can answer it right now. It's from Guglielmo Iozia. Sorry if I'm pronouncing not correct. Thank you, Professor Galar, for this presentation. Data scientists, fresh graduates, and experienced professionals both feel fascinated by doing ML and AI in the consumer space, but often ignore the challenges of doing the same in the industrial space. As am I an AI professional working in the biotech manufacturing, I got the same passion on this as yours.
Yeah, I think it's a more reflection rather than a question, but I would say that it's definitely when we go for this difference between consumer and industry, it's good that we extrapolate the similarities, that we have some similarities for sure, because the assets and the humans, they have to deliver similar services as profiling and prediction. But as I mentioned, one important point is the difference between the nature of the data. In the consumer, basically, is human produced data, and in the assets is machine generated data. And the amount of information in both